On April 19, 1971, the Soviet Union launched an ambitious venture that would forever change the trajectory of space exploration. Salyut 1, the world's first space station, was sent into orbit from Baikonur Cosmodrome in Kazakhstan, marking a monumental achievement in human history. This groundbreaking mission weighed approximately 18.5 metric tons and measured about 20 meters in length, with a pressurized volume of 90 cubic meters. Salyut 1 was designed to be a laboratory in the sky, equipped with 2 solar panels for power generation. The station included 2 habitable modules, the transfer compartment and the main working compartment. The transfer compartment was where spacecraft would dock, while the main working compartment served as the living and working area for cosmonauts. Salyut 1 remained in orbit for about 5 months, during which time it faced numerous challenges that would ultimately pave the way for future space stations. Despite these hurdles, the launch of Salyut 1 marked a significant milestone in the history of space exploration, setting the stage for an era where humans could live and work in orbit. This groundbreaking mission laid the foundation for future advancements in space technology. As we delve deeper into this remarkable story, we will explore the intricacies and triumphs of this pioneering mission that opened a new chapter in human space exploration. Stay tuned to discover how Salyut 1 faced its challenges head-on and how it laid the groundwork for future space stations, shaping our understanding of life in orbit. This launch was not just a triumph of engineering, but a testament to human ingenuity and the relentless pursuit of exploration beyond Earth's boundaries. With a length of 15.8 meters and a diameter of about 415 meters, Salyut 1 was relatively compact, but ingeniously designed to serve its primary mission. The station's dimensions were carefully chosen to support the vast array of scientific experiments it was tasked with conducting in microgravity. Scientific research in space had always been a dream for scientists, and Salyut 1 was built to make that dream a reality. Imagine the possibilities: studying materials without gravity's interference, observing biological processes in zero-G conditions. Salyut 1 was not just a technological marvel, it represented a monumental leap forward for the field of space science. Despite its relatively short lifespan, Salyut 1 laid the groundwork for future advancements in space technology and exploration. To put this into perspective, imagine attempting to navigate a ship without a rudder. The Soyuz spacecraft, designed to ferry cosmonauts to and from Salyut 1, were plagued with technical issues that made docking impossible. Despite multiple attempts, no crew ever successfully docked with Salyut 1 due to these persistent technical problems. This lack of a docking system was a critical flaw that prevented any human presence on board. The control system of Salyut 1 allowed for both manual and automated control, but the absence of a reliable docking mechanism rendered these capabilities moot. Salyut 1 completed 4758 orbits around Earth during its operation, but it remained largely inaccessible to crewed missions due to this critical flaw. The station relied on battery systems for power during periods without sunlight, showcasing its advanced design despite the limitations imposed by the lack of a docking mechanism. This failure to accommodate crewed missions underscored the significant challenges faced by Salyut 1 and set the stage for future endeavors that would address these critical flaws. One such challenge manifested in the tragic fate of Soyuz 11, the second crewed mission to attempt docking with Salyut 1. Their mission: to board Salyut 1 and continue the vital scientific research initiated by their predecessors on Soyuz 10. However, their mission was destined to end in tragedy. As the crew prepared for re-entry on June 29, a catastrophic event unfolded, a cabin pressure loss that led to the tragic perishing of all 3 cosmonauts. The exact cause of this pressure loss remains a subject of investigation and speculation. What is clear, however, is the profound human cost of this technical challenge faced by Salyut 1. Their loss underscored the high stakes and significant risks inherent in pushing the boundaries of space exploration. Despite this tragedy, the lessons learned from Salyut 1 would pave the way for future Russian and international space stations. The journey of human exploration in space is marked by both triumphs and setbacks, each shaping the next chapter in our cosmic story. Despite its eventual loss, Salyut 1 paved the way for future space stations. The primary goal of Salyut 1 was to test and verify long-term space habitation. A fire on board led to the decision to redesign future stations with improved safety measures. Salyut 1's main legacy lies in its pioneering role for subsequent Soviet and Russian space stations like Mir and the International Space Station. The lessons learned from the setbacks of Salyut 1 were crucial in shaping these later successes. Each step forward builds upon the lessons of the past, forging a path into the unknown. And so, Salyut 1's legacy endures as a testament to human resilience and innovation. The groundwork it laid continues to support our endeavors in space, guiding us toward new horizons. 2 years before NASA launched Skylab, the Soviet Union made history with Salyut 1. Designed to accommodate up to 3 cosmonauts at a time, this pioneering space station marked the dawn of a new era in space exploration. The groundbreaking features of Salyut 1 didn't just serve its own mission, they laid the foundation for future space stations. Salyut 1's ability to support a crew of 3 was a significant advancement that influenced later designs. Though the station faced its own setbacks and challenges, its innovations paved the way for future successes in space exploration. The Soviet Union's launch of Salyut 1 preceded NASA's Skylab program by 2 years, demonstrating the competitive nature of space exploration during that time. These innovations lived on in subsequent missions, guiding us toward new horizons and pushing the boundaries of human exploration beyond Earth's atmosphere. Beyond its technological innovations, Salyut 1 also paved the way for advancements in space medicine. Aboard Salyut 1, cosmonauts conducted medical research that would have far-reaching implications for future space missions and the field of space medicine. One key area of study was human physiology and zero gravity. Cosmonauts observed how microgravity affects the human body, from muscle and bone density to cardiovascular health. The results of these experiments were crucial in understanding the long-term effects of space travel on the human body, laying the groundwork for future research. Specifically, cosmonauts documented changes in their vision, which helped identify a condition now known as spaceflight, associated neuroocular syndrome, SANS. This condition can cause flattening of the ocular globe and changes in the optic nerve, which can lead to permanent vision impairment if not properly managed. Further experiments on Salyut 1 involve studying the impact of space radiation on human health. Cosmonauts recorded data on their exposure to cosmic rays and other forms of radiation which are more prevalent in space than on Earth. These findings have been instrumental in developing protective measures for future astronauts, ensuring their safety during long-duration missions. The medical research conducted on Salyut 1 set a precedent for subsequent space stations and the International Space Station, ISS, where more comprehensive studies have been carried out. Salyut 1's pioneering work in space medicine has paved the way for understanding and mitigating the challenges of human space exploration, making future long-duration missions possible. While this concept seems commonplace today, it was a groundbreaking development in 1971. These solar panels allowed Salyut 1 to generate its own power from sunlight. The advancements made possible by Salyut 1, such as solar power generation and life support systems, became cornerstones of space technology. These innovations have enabled longer duration missions and the establishment of permanent human habitation in space. As we look back at Salyut 1, it's clear that its technological strides were foundational in advancing our understanding and capabilities in space exploration. Its pioneering work has echoed through subsequent missions, reflecting the remarkable progress we've made since that first step into space. It set the stage for international cooperation in space exploration through early attempts like the Inter-Cosmos program. The Inter-Cosmos program was an agreement between Soviet and Eastern Bloc countries for cooperation in space exploration established during the early 1970s. This collaboration facilitated the exchange of scientific experiments and technology between participating nations. By allowing other countries to send their own payloads on Soviet spacecraft, it fostered a spirit of shared discovery in space research. For example, the Czechoslovak S-1 experiment, which studied the behavior of liquids in microgravity, was one of the many international collaborations facilitated by Salyut 1. Although initial attempts at cooperation faced significant challenges, they laid the groundwork for future joint missions. These early steps towards international space cooperation were essential for the success of subsequent space stations, including the International Space Station, ISS. The ISS, a collaborative effort involving numerous countries, has benefited greatly from the lessons and foundations established by Salyut 1. Its innovative design elements provided crucial insights into the architecture of later space stations. One key feature was its solar panels, which generated power for the station's operations. This design was carried forward into later stations such as Mir and the ISS, where solar arrays became essential for sustaining long-term missions in space. Salyut 1 also included a pressurized transfer compartment to facilitate docking with visiting spacecraft. This design was refined and expanded upon in subsequent stations, allowing for more efficient crew transfers and supply deliveries. One of the most significant improvements based on Salyut 1's lessons was the development of a robust docking system. The tragic loss of the Soyuz 11 crew highlighted the importance of reliable and safe docking procedures, leading to significant advancements in this area. These systems laid the foundation for more sophisticated life support technologies used in later stations like Mir and the ISS, ensuring that astronauts could live comfortably in space for extended periods. Salyut 1's influence is evident in the International Space Station, where advanced life support systems and efficient docking procedures are integral to its operations. By learning from Salyut 1's successes and failures, engineers were able to create safer and more sustainable environments for future astronauts. The design innovations pioneered by Salyut 1 have solidified its legacy in space exploration, serving as the foundation for groundbreaking advancements in space station design. As we gaze upon the stars, we can appreciate that the humble beginnings of Salyut 1 have paved the way for an extraordinary future in space exploration. For instance, the station carried instruments for studying the effects of microgravity on various materials, which laid the groundwork for future space research programs. In biology, Salyut 1's experiments included studies on plant growth and development in microgravity. These biological experiments were crucial, as they provided insights into how life can adapt to space conditions, paving the way for future space research programs. Salyut 1 also conducted Earth observation experiments, capturing valuable data about our planet from space. These observations were vital for understanding various environmental phenomena and laid the foundation for future satellite-based studies. Through these scientific advancements, Salyut 1 demonstrated its pivotal role in advancing space science, showcasing the practical benefits and innovations that came from its groundbreaking mission. By investing in space technology, the Soviets aimed to bolster their industrial capabilities and technological prowess on Earth. The development of advanced rocket systems and satellite production techniques were key benefits of the Salyut program. These advancements not only supported space exploration, but also had significant applications in terrestrial industries. For instance, the precision engineering required for reliable spacecraft translated into improved manufacturing processes in various sectors. Investing in Salyut 1 also provided an economic edge in the global space race, demonstrating the Soviet Union's capability to lead in cutting-edge research. The lessons learned from Salyut 1 laid a solid foundation for future space missions, highlighting the strategic importance of early investments in space technology. By showcasing their ability to innovate and succeed in challenging conditions, the Soviets set a precedent for future space programs. Thus, the economic implications of Salyut 1 extended far beyond its initial mission, establishing a legacy that continues to influence space exploration today. Its launch marked a significant milestone in the Soviet Union's quest for technological superiority during the space race. In the context of the Cold War, Salyut 1 was more than just a scientific outpost. It served as a powerful symbol of Soviet technological prowess and ambition. The Soviet Union used the station to demonstrate its technological superiority over the United States. As a symbol of Soviet achievement, Salyut 1 played a crucial role in international relations during the Cold War. Its mere existence was a statement of Soviet supremacy in space exploration. This perception influenced international relations and the balance of power during the Cold War era. These later space stations built upon the foundation laid by Salyut 1, further cementing the Soviet Union's pioneering role in space exploration. Salyut 1 served as a powerful political tool, influencing global perceptions of Soviet technological prowess and ambition. Despite these setbacks, Salyut 1 inspired a new generation of scientists and engineers. Its bold mission captured the imagination of young people across the Soviet Union and beyond, fueling interest in space exploration and related fields. The station's depiction in Soviet culture was notable. Artists and writers often used it as a symbol of technological prowess and human ambition. Its story was told in films, books, and paintings, all contributing to the mythos surrounding Salyut 1. Soviet media frequently covered the station's missions, both the successes and the failures. This transparency helped educate the public about the complexities of space exploration, while also celebrating the achievements of Soviet scientists and engineers. The cultural impact of Salyut 1 extended beyond the Soviet Union. Its launch was a major event in global space history, demonstrating the potential for long-term human habitation in space. This inspired international interest and cooperation in space exploration. The cultural significance of Salyut 1 lies in its ability to captivate the public imagination and foster scientific curiosity. It demonstrated that even with setbacks, pioneering efforts can lay the groundwork for future achievements. In the end, Salyut 1's story serves as a reminder of humanity's enduring drive to explore and understand the cosmos. Its cultural impact continues to resonate, inspiring new generations to look up at the stars with wonder and ambition. Perhaps most importantly, Salyut 1 showed that even in the face of failure, bold ventures can ignite a collective spirit of innovation and discovery. One of Salyut 1's primary goals was to conduct biological studies in microgravity. By studying how organisms behave in space, scientists could gain insights into the long-term effects of living in zero gravity. These studies laid the foundation for future research on board subsequent space stations, including more complex experiments and observations that couldn't be done on Earth. Salyut 1 also hosted technological experiments aimed at understanding how materials behave in space. This included examining the properties of metallic alloys and other substances under microgravity conditions. By studying how materials solidify or react differently in space compared to on Earth, scientists could advance manufacturing processes and develop new materials with unique properties. These early space station experiments set the stage for more sophisticated research on subsequent stations like Mir and the International Space Station. The data collected on Salyut 1 provided a foundation for understanding how living and working in space affects both humans and materials. The launch of Salyut 1 marked the beginning of a new era in space exploration, but it was not merely a Soviet endeavor. This inaugural space station facilitated international cooperation, hosting joint experiments and observation projects that involved various countries. Among the nations collaborating with the Soviet Union on these ventures were Romania and Poland. The cosmonauts aboard Salyut 1 conducted biological experiments, studying the effects of microgravity on different life forms. These collaborative efforts provided valuable data that laid the groundwork for future international space research missions. The joint observations and experiments on Salyut 1 set a precedent for cooperation, paving the way for subsequent stations like Mir and the International Space Station. For instance, the International Space Station today hosts astronauts from numerous nations, all contributing to a common goal of advancing space science. This global collaboration stands as a testament to the pioneering spirit that Salyut 1 embodied, marking the first steps toward unified space exploration. Salyut 1 not only advanced our understanding of life and materials in space, but also demonstrated the power of international cooperation in tackling cosmic mysteries. Despite its eventual deorbit, Salyut 1 left behind an enduring legacy that continues to inspire and guide future space missions. As Salyut 1 soared into orbit, it marked a turning point in space exploration. The Soviet Union's groundbreaking endeavor faced challenges that would ultimately lead to significant technological advancements. These solar panels were a pioneering solution to the complex problem of maintaining power in space. This extensive time in orbit provided valuable data and insights into the efficiency of solar power systems in space. The life support systems onboard Salyut 1 were another area of technological advancement. These systems provided air, water, and waste management for the cosmonauts, demonstrating the crucial importance of sustainability in long-term space habitation. Despite initial setbacks with docking attempts by Soyuz missions, the lessons learned from these challenges laid the foundation for future advancements. Its pioneering spirit continues to inspire new generations of space explorers as they venture into the cosmos. One of Salyut 1's most notable features was its modular construction, comprising two main sections, the transfer compartment and the main working compartment. The transfer compartment served as a docking port for spacecraft, facilitating crewed missions to the station. The main working compartment provided living quarters and scientific research facilities. These design elements, modular construction, living quarters, and sustainability features were crucial for subsequent space stations like Mir and the International Space Station. For example, the International Space Station, ISS, features a similar modular design, allowing for the continuous expansion and upgrade of its living and working spaces. The concept of long-term habitation introduced by Salyut 1 has been further refined in the ISS, which supports a continuous human presence in space. Despite facing significant challenges and ultimately being lost, Salyut 1's legacy lives on in the ongoing exploration and development of space habitats that will enable humanity to venture deeper into the cosmos. The visionary design elements pioneered by Salyut 1 have laid the foundation for future space stations aimed at long-term occupancy and further exploration of the universe. As we look towards the future of space exploration, it is clear that Salyut 1's groundbreaking innovations in space habitation concepts will continue to inspire and guide new generations of space explorers. And so, the pioneering spirit of Salyut 1 endures, shaping the course of human endeavors in the vast and wondrous cosmos. Despite its early setbacks, Salyut 1's legacy extends far beyond its initial missions. Amidst the vast cosmos, it pioneered a new frontier, space agriculture. This pioneering venture aimed to understand how plants respond to life without gravity's pull, a crucial step forward for future space habitats. As cosmonauts tended to these delicate greens, they observed fascinating adaptations and unexpected challenges. The insights gained were invaluable. Those early trials on Salyut 1 laid the groundwork for more advanced agricultural projects aboard later space stations. For instance, the Mir space station built upon these initial experiments, exploring not just plant growth but also food production in zero gravity. The International Space Station, too, has benefited from the lessons learned aboard Salyut 1. Today's astronauts cultivate lettuce and other vegetables, Thus, Salyut 1's legacy lives on, shaping the future of space agriculture and ensuring that humans can one day sustainably explore the cosmos. And so, amidst the stars, Salyut 1's pioneering spirit continues to flourish, nurturing life far from Earth's blue embrace. The early days of space exploration were filled with enthusiasm and ambitious goals, but little thought was given to the long-term consequences of launching objects into orbit. As more missions followed Salyut 1, the skies around Earth grew cluttered with debris that could potentially collide with active satellites and space stations. The Soviet Union recognized the urgency of addressing this issue and began developing mitigation strategies to manage space debris more effectively. One early approach was to design spacecraft with built-in redundancies that allowed for safe disposal of malfunctioning components without releasing them into orbit. Additionally, ground control teams were trained to monitor and predict the trajectories of discarded objects, ensuring that they did not pose a threat to future missions. These early mitigation efforts paved the way for more advanced debris management techniques used in later Soviet and Russian space missions, such as Mir and the International Space Station. By learning from the challenges posed by Salyut 1, the Soviet Union took significant steps toward ensuring safer and more sustainable space operations in future missions. And so, amidst the growing complexity of space exploration, Salyut 1's pioneering spirit continues to guide the way toward a safer and more sustainable future among the stars. Psychological studies conducted during these missions revealed crucial insights into the effects of microgravity on human behavior. Cosmonauts experienced spatial disorientation, a common phenomenon in space. Observations noted changes in perception and balance, highlighting the need for specialized training to adapt to weightlessness. These findings were pivotal in shaping future crew health management protocols. The crew also reported feelings of isolation and confinement, underscoring the psychological challenges of prolonged spaceflight. These early observations highlighted the importance of crew mental health in long-term missions. The Soviet space program's holistic approach included not just technical advancements, but also psychological well-being. The lessons learned from these pioneering missions continue to guide space exploration today, emphasizing the importance of a comprehensive approach to long-term habitation in space. As we look to the future of space exploration, understanding the human aspect of prolonged spaceflight remains a critical component. The space station's robotic arms were designed to assist cosmonauts with tasks that would have been difficult or impossible to perform manually in the weightless environment. These automated systems not only helped with the handling of delicate equipment, but also played a vital role in the maintenance and repair of the space station's infrastructure. The ISS, for example, features sophisticated robotic systems that handle tasks ranging from scientific research to routine maintenance and even the capture of visiting spacecraft. These robotic advancements are a testament to the foresight and innovation displayed by the Soviet engineers who designed Salyut 1 systems. Without the trailblazing work done on Salyut 1, many of the automated processes that keep modern space stations running smoothly would not be possible today. The technological innovations spurred by Salyut 1 have had an enduring impact on the automation of space missions, making them safer and more efficient for future generations of astronauts. As we continue to push the boundaries of what's possible in space, the legacy of Salyut 1 serves as a reminder that even the smallest steps can lead to monumental advancements. And this is where the story of Salyut 1 becomes truly fascinating. It paved the way for future space stations like Mir and the ISS, demonstrating how early innovations can shape the course of history. One of the most critical aspects of Salyut 1, which paved the way for future space stations like Mir and the ISS, was its environmental control systems. These systems were essential for maintaining a habitable environment for the cosmonauts aboard the space station. This included systems for regulating the temperature within the station. Despite these challenges, the lessons learned from Salyut 1's environmental control systems were invaluable and directly contributed to the success of future long-duration space missions. These early innovations laid a crucial foundation that would shape the course of space exploration history. And as we explore the legacies of such pioneering efforts, we see how each small step forward builds towards a greater understanding and capability in our quest to unlock the mysteries of space. One of the most innovative features of Salyut 1 was its use of solar power systems, a groundbreaking approach in space exploration that would set the stage for future advancements. This dual system ensured that the spacecraft had a reliable source of energy, enabling it to continue its mission even when solar power was not available. However, utilizing solar power in space presented significant challenges. The panels needed to be highly efficient and durable enough to withstand the harsh conditions of the cosmos. The solar panels on Salyut 1 were designed to endure extreme temperatures, radiation, and micrometeoroid impacts, which could easily damage or degrade their performance. These advancements allowed subsequent spacecraft to rely on more sustainable energy sources, reducing dependence on finite fuel supplies. The legacy of Salyut 1's innovative approach to power generation continues to shape the future of space exploration, demonstrating that even in the vast expanse of space, sustainability and efficiency are paramount. Salyut 1 was equipped with sophisticated antennae designed to transmit data back to Earth. These antennae played a crucial role in ensuring that the cosmonauts aboard the space station could communicate effectively with mission control. The primary method of data transmission involved using radio waves to send signals back to Earth. This method was reliable and efficient, allowing for real-time communication between the space station and ground control centers. In addition to radio waves, Salyut 1 also utilized other data transmission methods to ensure robust communication links with Earth. These methods included using satellite relays and high-frequency transmissions. From Earth, mission control centers monitored Salyut 1's communication systems closely. They used ground-based tracking stations to maintain continuous contact with the space station and ensure that all data transmissions were received correctly. Despite facing significant challenges, Salyut 1's communication systems proved to be reliable and essential for any future space station operations. They paved the way for more advanced communication systems in subsequent Soviet and Russian space missions. The importance of robust communications cannot be overstated, as they are vital for ensuring the safety and success of any mission in space. As we look to the future of space exploration, the lessons learned from Salyut 1 remain incredibly valuable. Ultimately, the communication systems of Salyut 1 demonstrated that even in the vast expanse of space, maintaining a reliable link to Earth is paramount for any successful mission. Maintaining orbit around Earth is no simple task, especially for a station like Salyut 1. Propulsion systems are the backbone of any orbital mission, enabling spacecraft to maneuver and stay in their intended paths. Salyut 1 was equipped with thrusters designed to fire short bursts of propellant. These thrusters were crucial for maintaining the station's orbit and making necessary corrections. The fuel used in these thrusters was a combination of nitrogen tetroxide, also known as N2O4, and unsymmetrical dimethylhydrazine, or UDMH. These propellants ignite on contact to produce a high-pressure gas that pushes the spacecraft in the desired direction. The precise control of these thrusters was essential for keeping Salyut 1 on its intended orbital path, as even a slight deviation could lead to drifting off course. Despite the challenges, the propulsion systems of Salyut 1 performed reliably during its operational lifespan, demonstrating the foundational role of such systems in any orbital mission. Without these crucial systems, maintaining a stable orbit would be nearly impossible, underscoring their importance for future space stations as well. This legacy continues to influence the design and operation of modern spacecraft like the International Space Station, ISS, which also relies heavily on thrusters for maneuverability and orbit maintenance. One of the key lessons learned from the fire was the importance of advanced simulation techniques. These simulations help astronauts prepare for potential emergencies and malfunctions in space. The experience with Salyut 1 also led to the development of new protocols for astronaut health monitoring. These protocols ensure that the physical and mental well-being of crew members are closely monitored during their time in space. These advancements have practical applications for preparing humans for long-term space missions. By learning from the challenges faced by Salyut 1, future astronaut training has become more comprehensive and effective. The International Space Station, ISS, which continues the legacy of Salyut 1, benefits from these improved training methods. Astronauts are better equipped to handle emergencies and maintain their health during long-duration missions. A key aspect of Salyut 1's mission was the development of high-resolution cameras and innovative Earth observation techniques. Salyut 1 was equipped with cutting-edge camera technology that allowed cosmonauts to capture detailed images of Earth's surface from orbit. These high-resolution cameras were a significant advancement in the field of remote sensing, enabling scientists to study natural resources and monitor climate changes with unprecedented precision. For instance, the cameras on Salyut 1 could capture images with a resolution high enough to distinguish between different types of vegetation and monitor deforestation. This capability was crucial for tracking changes in the Earth's biosphere and understanding the impact of human activities on the environment. Moreover, Salyut 1's cameras were instrumental in developing techniques for monitoring natural resources such as water bodies and forests. The data collected from these observations provided valuable insights into the health of our planet's ecosystems and the sustainability of its natural resources. The pioneering work done on Salyut 1 paved the way for more sophisticated Earth observation systems used today by various space agencies around the world. These modern systems build upon the innovations first developed on Salyut 1, further refining our ability to monitor and protect the Earth's environment. Thus, the legacy of Salyut 1 continues to influence and enhance our understanding of the planet we call home. The station's air recycling system was particularly innovative, converting the carbon dioxide exhaled by cosmonauts back into breathable oxygen. This closed-loop system ensured that the crew could survive extended periods in space without needing resupplies. Water was another critical resource managed by Salyut 1. The station's water purification systems were designed to collect and recycle water vapor from the atmosphere, ensuring that cosmonauts always had access to clean drinking water. Waste management was also a significant challenge addressed by Salyut 1. The station's systems were capable of collecting and storing waste efficiently, preventing any buildup that could threaten the crew's health. In essence, Salyut 1's innovations in life support systems marked a turning point in space exploration, one that ensured that future missions could focus on scientific research and habitation without worrying about basic survival needs. One of the early experiments conducted on board Salyut 1 involved growing crystals in microgravity. The Soviet cosmonauts found that the lack of gravity allowed them to grow larger, more perfect crystals than could be achieved on Earth. This discovery sparked interest in the potential for zero-gravity manufacturing processes. Imagine a future where pharmaceutical companies can produce more effective medicines by growing flawless crystals of active ingredients. The possibilities are vast, from improving the efficiency of electronic components to creating superior materials for spacecraft construction. Beyond crystals, Salyut 1 also hosted experiments in manufacturing other materials and products that could only be produced effectively in the unique environment of space. Although many of these early efforts were exploratory, they laid the groundwork for more advanced studies on later stations like Mir and the International Space Station. The legacy of Salyut 1 is not just in the history books, but also in the innovative space manufacturing techniques that continue to be developed today. The development of these advanced materials was driven by the need to create a space station that could withstand the rigors of space while maintaining functionality and efficiency. These lightweight materials not only reduced the overall mass of Salyut 1, but also ensured that it could operate effectively in the challenging environment of microgravity. One of the key innovations was the use of composite materials that provided strength with minimal weight. These composites, often made from combinations of metals and lightweight alloys, were instrumental in constructing the habitable modules of Salyut 1. For instance, the composite materials developed for Salyut 1 found their way into the construction of Mir and the ISS, ensuring that these later stations were lighter, more efficient, and better equipped to handle the demands of long-term space habitation. The technological advancements in space materials science sparked by Salyut 1 have had a profound impact on the entire field of space exploration. They have enabled longer missions, greater scientific discovery, and more efficient use of resources. The story of Salyut 1 serves as a testament to the power of pioneering efforts in space exploration and the enduring value of technological advancements that continue to shape our understanding and capabilities in space. In the grand scheme of human achievement in space, Salyut 1 stands out not only as a historic first, but also as a catalyst for future innovation and discovery. Initial experiments on Salyut 1 focused on food preservation. In space, where there is no gravity or atmosphere to slow down the decay of perishable items, preserving nutritious food becomes crucial. Scientists needed to find ways to ensure that astronauts received adequate nutrition during their missions. This led to innovative methods of food preparation and storage that could maintain the nutritional value of the food over long periods. Lessons learned from Salyut 1 shaped future space food programs. These early experiments revealed the importance of not just preserving food, but also tailoring diets to meet the specific nutritional needs of astronauts in microgravity. The insights gained from Salyut 1 about space food systems proved invaluable for subsequent missions. They highlighted the need for comprehensive life support systems that could sustain human life over extended periods in the harsh environment of space. The practical benefits of Salyut 1's research on sustaining human life in space cannot be overstated. By understanding and addressing the challenges of long-duration missions, we paved the way for even more ambitious explorations into our cosmic neighborhood. Among its groundbreaking missions were early space manufacturing experiments designed to test new processes and materials in microgravity. For instance, the growth of protein crystals was a key focus. In Earth's gravity, these delicate structures can be difficult to study due to their tendency to clump together. However, in microgravity, the absence of Earth's pull allows for more controlled and precise crystal formation, a significant advancement for scientific research. This breakthrough paved the way for other innovative materials to be tested in space, furthering our understanding of material science in zero gravity. Salyut 1's contributions didn't stop at crystallography. It also facilitated the study of other materials and processes that thrive in microgravity. By understanding how various substances behave in microgravity, scientists can develop new pharmaceuticals, better electronics, and even improved materials for space exploration itself. Salyut 1's pioneering work underscores the incredible potential of space-based manufacturing, a field that continues to expand our technological horizons today. Its legacy endures, guiding us into an era where space is not just a frontier but also a laboratory, a place where we can manufacture the future. On board Salyut 1 were advanced optical systems designed to observe the cosmos. These systems allowed scientists to study celestial phenomena from a unique vantage point, free from Earth's atmospheric interference. Data collected by these optical systems were transmitted back to Earth through sophisticated communication systems. This data provided valuable insights into the universe that would have been impossible to gather from ground-based telescopes. Through its pioneering role, Salyut 1 not only advanced our understanding of the cosmos, but also demonstrated the potential for long-term space habitation and scientific research in orbit. The technologies developed and tested on Salyut 1 continue to influence modern space telescope technology, enabling scientists to peer deeper into the universe than ever before. As we look back at this groundbreaking mission, it is clear that Salyut 1 marked a significant milestone in space exploration, a testament to the power of human curiosity and technological innovation. In an era where space is both a frontier and a laboratory, the legacy of Salyut 1 serves as a reminder that our exploration of the cosmos is just beginning. Delivering supplies to Salyut 1 was no simple task. There were no established docking systems for crewed missions. Without a reliable means to deliver supplies, Salyut 1 was effectively stranded in orbit. This mishap highlighted the critical need for precise and fail-safe docking mechanisms in space logistics. Subsequent missions, like Soyuz 11, carried improved technology but faced additional setbacks, including the tragic loss of all 3 cosmonauts in June 1971. The failure of Soyuz 11 underscored the importance of robust safety measures and reliable resupply systems in space logistics. Despite these early setbacks, Salyut 1 paved the way for future innovations in space logistics. Advances like automated docking systems and improved resupply missions would not have been possible without the pioneering efforts of Salyut 1. These innovations set a precedent for more sustainable and efficient logistics strategies in space exploration. As the world watched Salyut 1 soar into orbit, it was more than just a historic feat. It was a harbinger of challenges yet to come. One of these significant hurdles was the issue of orbital debris management. This debris consisted not only of small fragments from the station itself, but also larger components that had been jettisoned during various stages of its mission. The Soviet scientists, while proud of their achievement, were acutely aware of the growing problem of space debris. They understood that each piece of debris posed a significant threat to future missions and the safety of astronauts. Initial guidelines for managing this space junk were swiftly drafted, focusing on minimizing the creation of new debris and mitigating existing risks. These early innovations included precise planning of equipment releases to avoid uncontrolled scattering and the development of procedures for safely disposing of unwanted materials. The legacy of Salyut 1 extends beyond its groundbreaking mission. It forced the space community to confront the realities of orbital debris management from the very beginning. The necessity of safe and sustainable practices in orbital debris management became a cornerstone in the blueprints for subsequent space stations, ensuring their longevity and safety. Among its innovative missions were early attempts at creating and processing materials in space. The cosmonauts aboard Salyut 1 tried to manufacture components essential for future space missions. One significant challenge they faced was the harsh environment of microgravity. Materials that behave predictably on Earth can act unpredictably in space. Understanding these behaviors is crucial for future manufacturing capabilities. Despite the hurdles, the lessons learned from Salyut 1 laid the groundwork for more complex and ambitious endeavors. The early experiments on board set the stage for future space manufacturing efforts. This journey is paving the way for more advanced and ambitious space manufacturing capabilities. Equipped with powerful telescopes and cameras, Salyut 1 enabled groundbreaking astronomical observations from orbit. One of the most significant experiments conducted aboard Salyut 1 involved studying the Earth's atmosphere and its interactions with the solar wind. This research laid the groundwork for future space telescope missions, including the Hubble Space Telescope, which built on these initial observations to provide unprecedented views of the cosmos. The lessons learned from the failures and successes of Salyut 1 have been invaluable in refining space-based observation methods, paving the way for the growth of astronomical research from orbit. In essence, Salyut 1 served as a crucial testbed for early space telescope technology, demonstrating that space-based observations could revolutionize our understanding of the universe. As future missions like Hubble continued to build upon these foundational experiments, the field of astronomy entered a new era of discovery and exploration. By the late 1960s, the space race between the United States and the Soviet Union was in full swing. Both superpowers were eager to prove their technological superiority by achieving significant milestones in space exploration. For the Soviet Union, this meant developing a comprehensive strategy for long-term space habitation. This strategic shift focused on establishing permanent space stations to support both military and scientific objectives. The primary goal was to create a reliable platform for conducting extensive research in microgravity conditions. The strategic decisions that led to Salyut 1 marked a pivotal moment in space exploration history. Salyut 1's pioneering mission continues to influence modern space research and development. Key among these was the cooperation with European countries. The European Space Research Organization, ESR, played a crucial role in providing technological expertise and equipment for Salyut 1. These collaborations were instrumental in overcoming technical challenges that the Soviet Union faced alone. Examining Salyut 1's journey reveals that international collaboration was a cornerstone of its success story. Without these collaborations, the mission might have faced insurmountable hurdles, underscoring the importance of global cooperation in space exploration. Looking back, it is clear that Salyut 1's legacy extends beyond its groundbreaking achievements to include the invaluable lessons learned from international partnerships. As we continue to reach for the stars, these collaborations serve as a reminder of what can be achieved when nations work together towards a common goal. Salyut 1's mission may have ended, but its spirit of collaboration lives on, guiding future endeavors in space exploration. In the vast expanse of the cosmos, it is these collaborative efforts that ensure we move forward together, one step at a time. Among the key experiments were observations of Earth and its atmosphere, providing valuable data for meteorological studies. Salyut 1 also housed advanced materials, science experiments, exploring how different substances behave in the unique conditions of space. The findings from these studies offered insights into new manufacturing techniques and potential applications for advanced materials back on Earth. One particular experiment involved the crystallization process of various metals and alloys in zero gravity. This research helped scientists understand the fundamental properties of metallic structures in space, which could be crucial for future spacecraft design and construction. The successful completion of these scientific missions aboard Salyut 1 marked a significant milestone in space exploration. It paved the way for future scientific research in space, contributing to our understanding of both the Earth and the cosmos. In this vast and ever-changing universe, it is these pioneering efforts that ensure we continue to push the boundaries of knowledge. One of the most notable studies conducted aboard Salyut 1 focused on how the human body adapts to prolonged exposure to microgravity. Researchers observed changes in vision, balance, and bone density among the cosmonauts who spent time on board. These findings laid the groundwork for understanding the medical challenges astronauts face during long-duration space missions, paving the way for future research and mitigation strategies. In particular, studies on Salyut 1 revealed that extended stays in microgravity can lead to bone loss and changes in cardiovascular function. Despite not having a successful crewed mission, the data collected from Salyut 1 provided valuable insights that have since been used to improve safety measures and health protocols for subsequent space missions. By exploring how the human body responds to the unique conditions of space, Salyut 1 advanced our knowledge and prepared us for future endeavors in space exploration. Salyut 1 was equipped with powerful propulsion systems that allowed it to maintain its orbit around Earth. These engines were crucial for keeping the space station on track and preventing it from drifting off into space. The type of propulsion system used in Salyut 1 was a liquid propellant engine, similar to those used in the Soyuz spacecraft. This type of engine uses a combination of liquid oxygen and kerosene to generate thrust. The power generated by these engines was sufficient to keep Salyut 1 in orbit for several months, demonstrating their efficiency and reliability. These propulsion systems set a precedent for future space stations, including the Mir station and even the International Space Station, ISS. For instance, the ISS uses similar liquid propellant engines to maintain its orbit around Earth, a direct legacy of the technology tested on Salyut 1. This legacy continues to enable humans to push further into the cosmos and uncover new scientific frontiers. Additionally, the station featured advanced water reclamation systems that collected and purified moisture from various sources. This allowed astronauts to drink recycled water, conserving precious resources in the closed environment of space. Waste management was another critical component. Salyut 1 employed systems that efficiently collected and stored waste products, preventing contamination within the station's confined spaces. Imagine living in a small apartment where every drop of water and breath of air must be recycled. This was the reality aboard Salyut 1. The cosmonauts' reliance on these life support systems underscored the necessity of such innovations for long-term space exploration. Their experiences aboard Salyut 1 highlighted both the challenges and the possibilities of life in space. Salyut 1's pioneering life support systems represent a testament to human ingenuity and resilience in the pursuit of understanding our universe. Beyond its pioneering life support systems, Salyut 1 also introduced advanced techniques for observing Earth from space. Among its sophisticated tools were Earth observation cameras and spectrometers, designed to capture detailed images and spectral data of the Earth's surface. These instruments allowed scientists back on Earth to analyze specific wavelengths of light reflected from various landscapes. By examining the unique spectral signatures of different environments, researchers could identify distinct features such as forests, deserts, and bodies of water. This innovative approach to Earth observation laid the groundwork for future missions focused on environmental monitoring and climate studies. The data collected by Salyut 1 not only advanced our understanding of Earth's ecosystems, but also paved the way for more sophisticated Earth observation satellites. These subsequent missions built upon the foundation set by Salyut 1, incorporating even more advanced sensors and technologies to monitor our changing planet with greater precision. Today, Earth observation techniques pioneered by missions like Salyut 1 are integral to global efforts aimed at addressing environmental challenges and climate change. Though Salyut 1 was a first step in this journey, its contributions continue to echo through the advancements made in space-based Earth observation techniques. By venturing into the unknown, Salyut 1 not only expanded our cosmic horizons, but also deepened our understanding of the home planet we cherish. Beyond its structural elegance, Salyut 1 boasted advanced radiation shielding, a critical feature for any long-term space habitat. This shielding safeguarded the cosmonauts from the potentially harmful effects of solar and cosmic rays, ensuring their safety during extended stays in orbit. Imagine the complexities of outfitting a space station with systems that would keep it operational for months at a time. Salyut 1's designers had to account for everything from life support systems to power generation, all while ensuring the safety and comfort of its occupants. Imagine navigating through the vast expanse of space without a crew on board. Salyut 1 was designed with state-of-the-art robotic systems that could manage every aspect of its operations, from power generation to waste management. At the heart of these systems was a sophisticated communication network that allowed ground control to monitor and adjust the station's functions remotely. This was a crucial step toward developing fully automated spacecraft. Consider that Salyut 1 was placed into orbit in April 1971, a time when space technology was still in its infancy. The fact that it could operate autonomously for months at a time is truly astonishing. Salyut 1's automated systems were a testament to the ingenuity and foresight of Soviet engineers. They paved the way for future unmanned missions and ensured that space stations could be maintained efficiently even in the absence of human presence. In October 1971, after completing its mission, Salyut 1 re-entered Earth's atmosphere and was lost forever. Yet, the innovations it brought to space exploration continue to echo through history. As we gaze into the night sky, we can take comfort in knowing that Salyut 1 and its groundbreaking automated systems laid the foundation for a future where space exploration knows no bounds. The challenges faced by these early automated systems were significant. Without a docking mechanism, Salyut 1 was inaccessible to crewed missions. Despite this, the lessons learned from these initial experiments would prove invaluable. The Soyuz spacecraft that attempted to dock with Salyut 1 encountered technical difficulties, highlighting the need for more robust automated systems. The cosmonauts aboard Soyuz 10 and later Soyuz 11 faced these challenges head-on. Beyond just testing automated docking systems, Salyut 1 also played a pivotal role in advancing the field of space medicine research. During its brief but influential time in orbit, Salyut 1 served as a laboratory for various medical experiments conducted by the cosmonauts. These included studies on how microgravity affects the human body and its systems. One of the key investigations focused on cardiovascular health in space. Cosmonauts underwent detailed heart rate monitoring to observe how weightlessness influences blood circulation and pressure. The data collected from these experiments provided valuable insights into the physiological changes that occur during prolonged spaceflight. This knowledge has been instrumental in designing countermeasures and exercises to mitigate potential health risks for future astronauts. In addition to cardiovascular research, Salyut 1 also hosted studies on the effects of microgravity on bone density and muscle mass. Cosmonauts were monitored for signs of bone loss and muscle atrophy, which are common issues in long-duration space missions. These findings have been crucial in developing exercise regimens and dietary guidelines specifically tailored to the unique environment of space, helping maintain astronaut health over extended periods in microgravity. Moreover, Salyut 1's pioneering medical research has influenced subsequent space missions and stations like Mir and the International Space Station ISS. Building on the lessons learned from Salyut 1, future space stations have continued to refine their approaches to space medicine. By understanding how human health is affected by prolonged exposure to microgravity, scientists are better equipped to support longer-duration space exploration and even the possibility of interplanetary travel. The groundbreaking efforts in medical research conducted aboard Salyut 1 laid the foundation for a deeper understanding of human health and microgravity, contributing to its groundbreaking role in space exploration. And so, while Salyut 1 may have faced significant challenges and ultimately met an early end, its pioneering medical research has left a lasting legacy that continues to shape the future of space medicine and exploration. The successful operation of Salyut 1 suggested that human habitation in space was not just possible, but potentially sustainable. This revelation piqued the imagination of visionaries who saw beyond scientific research. They began to envision a future where space stations could be used for more than just experiments. The idea of commercializing space started to take root in the minds of forward-thinking individuals. This sparked early thoughts about space tourism, a concept that seemed far-fetched but increasingly plausible with each successful mission like Salyut 1. These pioneering visions included potential uses for space stations that went beyond research and development. They imagined hotels in space where people could stay for leisure and enjoy the unique experience of weightlessness. While these ideas were still speculative at the time of Salyut 1's launch, they laid the groundwork for future applications of space technology that would go beyond scientific exploration. Though Salyut 1 met an early end, its legacy lives on in the ongoing quest to make space more accessible and inviting for future generations. The dream of space tourism, once just a glimmer in the eyes of visionaries, is now closer to reality thanks to the groundbreaking work done on Salyut 1. During its brief but groundbreaking tenure, Salyut 1 set several records, including the duration of cosmonauts' stay aboard the station. These missions faced numerous challenges, from technical issues to the physical demands of long-duration space travel. The lessons learned from these missions were invaluable. They shaped future designs for space stations, incorporating safety measures and technological advancements to ensure the well-being of cosmonauts on long missions. This pioneering spirit underscores the groundbreaking nature of Salyut 1, setting a new standard for continuous habitation in space and paving the way for future space stations. Crystal growth studies were among the first experiments conducted on board. In zero gravity, crystals grow without imperfections, providing valuable insights into materials science. Fluid dynamics studies also benefited from the weightless environment of Salyut 1. Researchers observed how liquids behave differently in space compared to Earth's surface, contributing to our understanding of fluid mechanics. The legacy of Salyut 1 continues to influence modern space science, paving the way for new discoveries and innovations in zero gravity. The unique environment offered by Salyut 1 enabled groundbreaking zero-gravity research that would shape the future of space exploration. Salyut 1 wasn't just about exploration, it was a pioneer in space manufacturing. Despite its eventual loss, the station laid the groundwork for future efforts. Inside Salyut 1, cosmonauts conducted experiments that tested the boundaries of what was possible in microgravity. One notable focus was the production of semiconductors. These materials, crucial for modern electronics, behaved differently in zero-G, allowing scientists to study their properties and behavior in ways never before possible on Earth. The results were groundbreaking. The unique environment of Salyut 1 enabled researchers to understand how microgravity affects the crystal growth and purity of these materials. But it wasn't just semiconductors that were manufactured on Salyut 1. The station also saw experiments involving other materials and substances. Salyut 1 may have been lost, but its legacy lives on. The station's pioneering work in space manufacturing has laid the foundation for more sophisticated research and development. As we gaze at the stars, it's humbling to realize that humanity's quest to harness the power of space is not just about exploration, but also about creating new possibilities in manufacturing. Beyond the breathtaking sight of stars, Salyut 1's true impact on space exploration lies in its contribution to astronomy. These advanced tools allowed scientists to peer deeper into the cosmos than ever before. With the ultraviolet telescope, astronomers studied the ultraviolet radiation emitted by stars and galaxies, providing insights that couldn't be obtained from Earth-based observations. Meanwhile, the X-ray spectrometer analyzed high-energy X-rays to uncover secrets about black holes and other celestial phenomena. The data collected during its operational period laid the groundwork for future space observatories and advanced astronomical research. Its legacy continues to inspire new generations of scientists aiming to unlock the mysteries of the cosmos. Beyond its groundbreaking role in space exploration, Salyut 1 also pioneered the field of space biology. In the microgravity environment of Salyut 1, scientists conducted numerous experiments to study the effects of weightlessness on various life forms. Plants were among the subjects of these experiments, revealing how they grow and behave differently in space compared to Earth. Researchers found that plants in microgravity exhibit peculiar growth patterns, with roots growing upward instead of downward. Crystal formation was another area of interest, as the absence of gravity allows for the growth of larger and more perfect crystals. The study of cellular behavior in microgravity provided insights into how cells function differently without the influence of Earth's gravity. These findings on Salyut 1 paved the way for advanced research in space biology, setting a precedent for future space stations and missions. While the station eventually lost its orbit, the knowledge gained from these experiments continues to be invaluable in advancing our understanding of life beyond Earth's atmosphere. Today, The scientific legacy of Salyut 1 endures, inspiring new generations of scientists to explore the mysteries of space biology. These pioneering efforts on board Salyut 1 not only expanded our knowledge, but also opened up new avenues for future exploration and discovery in the vast expanse of space. Despite the significant challenges faced by Salyut 1, its groundbreaking mission laid the foundation for future innovations in space exploration and ignited public imagination about the potential of orbital habitation. The initial concept of human presence in orbit as a form of tourism was sparked by the long-term effects of living in space. As humans lived and worked in orbit on Salyut 1, the idea of space as a destination for exploration and adventure started to permeate the public consciousness. The public began to imagine what it would be like to experience space firsthand, sparking early thoughts of space tourism and commercial ventures in orbit. This idea would later grow into more tangible concepts. Although the mission faced significant challenges, including a loss of contact and a tragic accident on Soyuz 11, the legacy of Salyut 1 endured. This groundbreaking mission paved the way for future innovations in space, including the idea of space as a destination for exploration and adventure. Despite the challenges and setbacks, Salyut 1's pioneering journey marked the beginning of a new era in space exploration that would eventually lead to more sophisticated concepts of orbital habitation and tourism.